And then on podcast will just be us being like, yeah, Bayesianism sucks. Go Popper.
I've been getting in trouble for swearing, so we should not swear.
No shit. Okay.
But I swore like 3 times in the middle of our conversation too. But everyone's been getting mad at me for that.
Are you still getting in trouble?
Yeah. Claudina's like, Vaden, you swore a whole bunch of times. I think I said fucking shit a couple times. I guess it sounds much more harsh in a podcast format than.
Yeah, that's true.
Yeah.
All right, welcome to another episode of Increments. Today we finally actually dive into what we promised a few episodes back during the Hubris of Computer Scientists, into the world of probability. And that'll probably turn a large portion of you off immediately, especially those of you who aren't ensconced in PhDs in technical disciplines. But honestly, I really urge you to try and stick around for this one, and especially the next one, just because I think the topic is of import, and for me personally, it really has changed my thinking, or at least challenged my thinking in a variety of ways. I don't think I realized how important the philosophy of probability is, just in terms of your day-to-day life and how you make decisions and how you think about ideas and their impact and what matters to you. And so it's amazing. I'm not sure if we get all of that across in these episodes, but these ideas will probably continue to lay the foundation for a lot of our future conversations and a lot of our future disagreements. So in as much as you can, I think it's really worth trying to hold on for this one. Unfortunately, the beginning, I would say, maybe not unfortunately, but we do start this episode with a bit of just a background of how different groups of people think about probability, and that might not be of interest to all of you, and so with that in mind, I've made chapter markers in the episode, and so if you get lost in that, or if you just don't want to deal with that sort of background at all, I urge you to just skip directly to the section entitled "The Philosophy of Probability," which is really where the rubber meets the road in terms of the impact of this on our daily lives. Vaden, do you want to say anything about how many times you get to prove me wrong in this terrible series of conversations?
Yeah, well, I guess according to Bayesian epistemology, there is no such thing as being proved wrong. There's just having your beliefs updated. And hopefully that pseudo joke will make a bit more sense to listeners by the end of the second episode. So I agree with everything you said. I just want to add a couple points. I guess the first is that if you're feeling a little lost in the beginning, completely fair. A lot of what we say actually comes from a presentation I gave, I guess, about a year ago, internally to my lab. And so there's going to be some slides that we'll put in the show notes. And so if you flip through the slides, hopefully that will lay a bit of foundation for the material we'll be covering in the episode. If you are a PhD student or a grad student kind of in data science or machine learning, like Ben had mentioned, I'm hoping that the second half will challenge you a bit, because I've had to search far and wide for a lot of these ideas. They don't actually come from the machine learning community. They come more from the philosophy and physics community. And so hopefully, if your background is more in CS and stats like mine is, there'll be some new stuff for you here as well. So there's 2 episodes we're going to be releasing. The first, I'd say, lays a lot of the background material. The second episode is going to be applying this material to a real-world example, and the main thing we'll be focusing on is existential risk and the effective altruist community. So stay tuned for that. Last, I believe there's some sound difficulties for this episode. We clearly are still figuring out what we are doing. Currently trying to understand how Audacity works. So expect improvements to the sound in the next few episodes. And with that, let there be no more of this ado, and play the show. Yeah, so we both attended a Zoom lecture on Thursday, which was a student of David Deutsch summarizing some of his recent work, where him and Deutsch were trying to kind of re-explain this disproof of probabilistic induction that Karl Popper and David Miller published in, I guess, the 80s. And so perhaps it's not important to go into the various details of what they discussed, but I'm just curious what your thoughts were in general with that lecture.
Yeah, no, I was probably less thrilled by it than you were, just because I think this new area is just new for me. And so just thinking about probabilities and the distinctions of different probabilistic frameworks and how this relates to epistemology in general is new territory that my mind is slowly engaging with. And so for that reason, I think I probably got less out of it than someone who is already familiar with the actual content. For me, it was just a good introduction to the community, and people were thinking along lines that, I guess thinking about problems in ways that are unfamiliar to me, and just introduced me to this new field of interpretations of probability, and also why this matters, right? Like before, I don't think it would have been obvious to me that the way you interpret probability is meaningful insofar as your view of the production of knowledge or anything is concerned. But now it's quite clear to me that these things are tied together pretty substantially, and just how far probability, the interpretation of probability and the probability calculus have infiltrated other disciplines and stuff, and how easy it is for our language to become probabilistic in nature when maybe it shouldn't, or at least when maybe we're not actually clearly thinking about what we mean when we try and start assigning probability values to different things. So it was interesting for me, but I can't say any of the specific content was particularly illuminating, because I'm still getting introduced to what's going on.
Yeah, I guess like one thing that I think is so interesting about this community is that it's almost completely disjoint from the Bay Area rationalist community. Like there's very little overlap between these two groups. And I think I was saying this to you in a previous conversation that perhaps it wasn't aired, that like I think a lot of our listeners and perhaps you and I ourselves, like we got into the Bay Area rationalist community kind of by stumbling upon Les Wrong and L.A. Yudkowsky's writing, and then from there kind of finding Slate Star Codex and reading Marginal Revolution and all these blogs and stuff, and just really getting high on this drug of rationality, right? And then when I discovered this other group, I realized like this is where the hard stuff is. If you really want the drug of rationality, you got to go deep into the world of David Deutsch and Karl Popper and David Miller and actually
this is the acid of rationality.
Yeah, and for some reason this community is dominated by Davids. There's like David Deutsch, David Miller, David Lewis, David Papineau, I think. So just follow the Davids. Is all. Just follow all
David's all the way down.
Yeah, David's all the way down. But yeah. So like, I guess we should start at the beginning. And so the subject is the philosophy of probability, and I started taking an interest in this, I guess, when I joined a Bayesian machine learning group in Tokyo, where you were as well with a different team. So we were both at Riken, and I was working with Imtiaz Khan. And you were doing discrete optimization stuff there?
Yeah, exactly, with Takanori Maehara there.
Nice.
It was lots of fun.
Yeah. And so that started the journey of me becoming really interested in Bayesian methods and Bayesian probability from a practitioner's perspective, like how you actually use it to solve real problems. But as I was reading more and more about it, I realized that was just one small, tiny aspect of the larger conversation about the Bayesian interpretation of probability, but then even larger than that, just the interpretation of probability itself. And so that started this rabbit hole of research into the various arguments and discussions and debates surrounding probability. And there's this paper that I think I found it just through Wikipedia, and I don't know if it's on Wikipedia anymore, but it's from the meteorology community. And so meteorologists obviously think about probability quite a lot because I have to use it for weather forecasting. And so the paper is called "The Diversity in Interpretations of Probability: Implications for Weather Forecasting." And in this paper, they say that there's many interpretations of probability, but none of them are free of internal contradictions and paradoxes.
Right.
And that just really fascinated me. And so that's kind of the space of what we're going to be hopefully talking about today, which is the various interpretations, their paradoxes, their contradictions, why there's such heated arguments between philosophers like all through the 20th century, and hopefully what the implications of these arguments are. But I think the chance of listeners getting lost is quite high. So we have to, I think, do a good job of keeping one another grounded and using real world examples and not using just arcane jargon, which also dominates the Bayesian world, like talking about likelihoods and priors and hierarchical empirical priors and all that. So we can't use any jargon. We have to make sure that we keep each other in check there. But
that sounds good. Also, just on that note, maybe it's worth giving slight background into like why people might give a shit about this, even if they're not that familiar with the world of probability and stuff.
Yeah.
Because I think it's easy. This was my experience as well at the beginning. I use probability as a tool all the time when I'm doing math or computer science and things like this. But then it's unclear the extent to which this, infiltrates your worldview and how others are thinking about the world around you until you really start diving into it. Maybe just like at least one concrete example of when, like, why probability really matters. And this is like a political example. So when Obama was in office, they were trying to find out where Osama bin Laden was. And they received some intelligence that he was in the compound in Abbottabad. Mm-hmm. And he sort of famously asked his advisors, like, what is your credence or what is your probability or what's your certainty that Osama bin Laden is in this compound, right? Like if we charge in there and he's not there, this could be a political disaster. But we obviously want to catch him. And so I'm trying to weigh the pros and cons of this situation. And so our interpretation of probability and what Obama means when he says, give me your certainty, give me your credence about whether he's in this compound or not, this comes to dominate our political landscape, right? Mm-hmm. And so obviously has huge import on like how our politicians are acting, especially in conditions of sort of radical uncertainty. Mm-hmm. And maybe just to give an example of like why the interpretation of probability actually matters in real life. And you might take a step back and ask, like, what does it mean for someone to even have 60% certainty that Osama bin Laden is in Abbottabad at that moment, right? Does that mean like he's there 60% of the time, or does that mean 60 out of 100 cases similar to this one, the target would be there? Yeah. What does it mean to say you're 60% sure? So this is, a situation in which your interpretation of what probability means has direct impact onto the situation. Yeah.
No, I think that's great. So let's maybe start right at the beginning. I thought one way we could perhaps organize the first part of this conversation is first by just talking about the ordinary everyday usage of the word probability, and then talk a bit about how mathematicians think about probability, and then talk about how philosophers think about probability. Maybe I can start by talking about my experience learning about this as undergrad in computer science. Most of us, when we think about the word probability, we kind of use it to mean something along the lines of chance, right? So if we say there's a chance it might rain tomorrow, that means there's various things that could happen tomorrow, and of the things that could happen, rain is included in that. But there's no certainty that it's going to rain tomorrow. Or we'd say the probability of a dice rolling 6 is 1 in 6. And that, I think, is quite intuitive for most people, that you're talking about if you were to repeatedly do this thing, so roll a dice, approximately 1/6 of the outcomes would be 6, say. Then the other way I think that the word probability is used in kind of common parlance is just as an alternative to certainty. So if you say, like, I'll probably get the job tomorrow, or I'm probably going to go for a run later, it's not that we're really making anything definitive about the set of all events. It's just a way to say, I'm not certain about some particular outcome. And so I went into computer science thinking about probability in these terms that has something to do with frequencies and chances and stuff. Do you remember learning about like probability is just you have shapes like squares and triangles and they're different colors? So this starts to, I think, bridge the gap between the common usage and the mathematical usage, where mathematicians don't think in terms of chance. They don't think in terms of frequencies. Even they tend just to think in terms of measure theory. So we should maybe say a little bit about measure theory, where if you Google measure theory, it's just like a bunch of notation and you're like, oh my God, this is so complicated. But I think it's actually not super complicated. If you, like the metaphor that I like to use is like an abstract fluid. Just imagine spreading an abstract fluid across a table, say. So why do I use the phrase abstract fluid? Because it's not a real thing. It's just that the intuitions we have thinking about fluids, I think, will allow us to think about how mathematicians refer to probability and how they think about probability. So let's say we have exactly 1 unit of this fluid, because 1 is an easy number to work with. And being a fluid, you can't have a negative amount of the fluid, so it has to always be positive. And if we're going to spread it across the table, we have to make sure we use all of it. There's can be none left over. So we can spread it however unevenly we like. We can put like 90% of the fluid on the first part of the table and then evenly spread the remaining fluid out over the rest of the table. And then if you imagine like breaking the table in half, if you have 90% on one piece, then you have 10% left on the rest of the piece. And that's measure theory. You have a finite quantity, it can't be negative, and it behaves roughly in accordance with what we would think it would behave if you take the set of events and split them into pieces and combine them up again. So then when you read the Wikipedia page about measure theory, you'll see all sorts of notation and stuff. But if you just think about kind of how a fixed quantity will behave if you distribute it across a bunch of events and it's conserved, then that's how mathematicians tend to think about probability. But notice... Nice,
that was pretty good. Pretty good, actually. Yeah. Having studied measure theory for a while, I've never actually heard it described as a fluid. So that was a...
does that match... Because you know measure theory, obviously. Does that match like how you would describe it?
Yeah, I'd say if anyone was lost, the details are pretty unimportant, but it's just, you have some space and you want to be able to put a function on it that just measures this space in some way. You want to be able to say things about how big this space is. So in Vaden's example, the space is the table. And now you can start measuring different aspects, different portions of the table in different ways. And as long as this measure just obeys certain sort of like logical axioms that we'd want, right? You can't measure can't have negative quantity, right? So it's always got to be like 0 or positive. And so it's just a very formal way to define size on some abstract space. That's all that's going on.
How does measure theory and probability theory relate? Probability theory is just a measure with unit 1, so it's just a normalized measure. So pretty straightforward there. But notice that in the mathematical discussion, there is no usage of the phrase frequency, randomness, chance, uncertainty. It's just a mathematical object that obeys certain properties. And the probability calculus, so you and I are probably going to use the phrase probability calculus quite a bunch in this conversation. That came before measure theory. So that is just essentially the sum and product rule. And the sum and product rule are super intuitive. Like, let's just use the dice example. What's the sum rule? The sum rule is if you want to figure out the probability of rolling, let's say, an even number, that's just going to be the sum of the individual probabilities of all the numbers which are even. So 1 over 6 is associated with rolling a number 2, number 4, and number 6. So you just sum all those up. And then, so that's the sum rule. And then the product rule is similar. It slightly maybe a little less intuitive to explain, but the product rule is basically if you have what's the probability of rolling an even number and a number which is divisible by 6. So the probability of the conjunction of two things. It just factorizes into the probability of rolling an even number given that you've rolled a number 6, and then the probability of rolling the number 6 itself. So it's just two very simple operations. And then the other kind of constraint is that the probability of a set of events has to sum to 1. Okay, so we have a mathematical formalism that came, I guess, like in the 1700s, 1800s, that just basically says you can write P, parentheses, capital A, close parentheses, and when you write these symbols, they're going to obey certain rules. Then measure theory came a little later with Kolmogorov, who put probability theory in a bit more of a firm footing, thinking about it in terms of dividing fixed quantity across a set of events, such that it obeys certain rules. And then we have the fact that this calculus is quite useful in describing real world things. So one thing that this calculus can describe is density in the physics sense, right? So you can use this concept to describe the density of certain objects, and that's why the phrase like probability density function is used, because you can use this calculus to describe density. You can also use it to describe frequencies. That's where the mathematics starts to become applied into these various domains. So that's a connection there. But where the philosophy piece comes in is that it turns out it's not as easy to apply this calculus to all of the things that people want to apply this calculus to. And I gave a presentation on this in my lab like about a year ago, and I kind of playfully referred to this as like the probability wars. And this is not agreed upon terminology whatsoever. It's just me being a little bit playful, where you have all these philosophers saying, I think we should interpret probability in this way or this other way. And then a bunch of other philosophers poking holes in all the other philosophers' interpretations. I think as say, an undergraduate studying this stuff in computer science or in mathematics, you quickly go from the first part of this conversation, which is just the ordinary usage, to the mathematical part of this conversation, which is studying the properties of measure theory. And you don't spend a lot of time on the philosophical side of this conversation. So machine learning, people will know about the book by Chris Bishop. It's kind of like the Bible in machine learning. And in Bishop's book, he gives like a paragraph and a half to discuss the philosophy and the philosophical interpretations. But most people just skip that. And so I really want to spend a lot of time focusing not on the mathematical stuff, which I think is will be familiar to some people and less interesting to other people, but on the philosophy. And so that's at least my attempt at structuring this conversation, I think, in a way that hopefully will prevent people from getting lost. So
okay, good. Okay, yeah. So we got, just to summarize here, we have everyday notions of probability that people typically come across in, say, high school or something, when they're just learning about math and they're learning about, like, what's the probability I pick a red ball out of a bucket or something. And in everyday usage, we sort of use notions of probability when referring to myriad different things. So whether it's chance, randomness, uncertainty, or belief, we kind of use the notions of probability to talk about all of these things. And so that's just like in common parlance what's going on. And then we have the mathematicians who sit down and really try and make notions of probability rigorous, and they tend to do this in terms of measure theory. So they just take some abstract space and they want to start measuring events on it. And so they think about probability in terms of taking, your outcome space, which for the dice example is maybe just like all the possible rolls of dice, and then they assign values to different rolls, and these are known as your probabilities. So these would be the measure you're putting on your sample space here. Mm-hmm. And then we have the philosophers who take a step back and are asking, how do we actually interpret probability? Is probability something manifest in the real world? Is it just some psychological interpretation of something in the world? Or like how should we actually think about probability? Yeah. And so in this conversation, we're mostly focused on the philosophical interpretation of what's going on.
Precisely.
And then, okay.
Cool. So if we're okay to move to the space of philosophical treatment of probability, the big two interpretations, let's say, would be the Bayesian interpretation and the frequentist interpretation. So now we're saying, okay, fine, we know what the probability calculus is. It obeys certain rules. Everyone agrees on those rules. There's absolutely no controversy there. The controversy emerges when people start trying to figure out how these rules map onto reality, the world that we actually live in. So let's highlight a particular problem with interpretation. So the frequentist interpretation says probability is what happens when you repeat an event a large number of times It's the ratio of certain events given all events. So the frequency of certain outcomes. Rolling dice is a really nice intuitive example. Throwing darts at a dartboard, intuitive example. But how do we apply that if we want to say things like the probability that the polar ice caps will melt in 2100 is 64%? Say this doesn't really work because this is something that's only going to happen once. Or if you don't like that example, we can use a different example, which is what is the probability that the theory of the Big Bang is true? Well, the Big Bang only happened once. We can't repeat the creation of the universe a multitude of times. But people want to be able to use phrases like probability to describe this. So that's one of the big, I think, problems with the frequentist interpretation, which is that it's not easily applied to single events. So then Bayesians say, okay, well, we're not going to consider probability to refer to the frequencies of events. We're going to instead think about probabilities as the belief rational agents have in certain propositions. So to understand this kind of treatment of probability, I think we should maybe mention Cox's theorems. Are you familiar with Cox's theorems?
Yeah, only from your slides, though.
Yeah. So
I'd never seen them before in any math class or anything. I mean, I guess it makes sense because it's a very non-mathematical interpretation of what's going on,
So Cox, C-O-X, he actually, sorry, let me take a step back. Let's say we want to solve the problem of assigning numerical values to beliefs that rational agents have in certain propositions. So first, this completely solves the concern about the polar ice caps melting, because to say the probability of the polar ice caps melting is to start talking about credences, right? So Cox basically said that if you have the goal of assigning scalar values to beliefs, we can call them credences, or I like the phrase, I think Cox used the phrase plausibilities. So rather than thinking about a probability of the polar ice caps melting, let's think in terms of the plausibility of a polar ice caps melting. He showed that if you if this is your goal and you have a couple reasonable axioms that as you get more evidence, the plausibility should go up of a proposition, and we'll say that absolute certainty is going to be indicated with 1, and absolute falsity, so we are absolutely certain that the polar ice caps will not melt, we'll represent that as 0. Then the credences of rational agents must obey the probability calculus, which we referred to earlier, that the sum and product rule, etc. So if listeners imagine a white sheet of paper in front of them and they write P parentheses, capital A, close parentheses, and then we think, well, what is the capital A representing? In the frequentist world, A is representing an event, so the event of rolling a 6 in dice. But in the Bayesian world, the capital A represents a sentence, a proposition, a statement, and P of A would represent the belief or the credence that a rational agent has in that sentence.
Let me just give one more summarization attempt here, just to make sure we're not losing people, or at least attempt at trying to losing people. Okay, so the philosopher asks, how do we interpret these probabilities? And one natural thing to do, as Vaden said, is to just associate them with the frequency of events. And this is naturally what I think a lot of people do when they think of probability. So your excellent example of rolling the dice, why do we think that rolling a 1 on a 6-sided die has probability 1/6? And typically this is because we think, like, well, in the long run, if I roll it a lot, this will happen approximately 1/6 of the time. And so this is this is the frequentist interpretation of probability, and this has to do with the frequency of events. And so as you pointed out, this has problems when you try and apply it to one-off events, things that only happen once, because then it's kind of meaningless to start asking about the probability of events. But what I found fascinating is, like, once you start digging into this literature, is not only that are there problems when you just try and apply it to other scenarios, there's sort of inherent problems just in the frequentist interpretation in and of itself. And, this has to do with, like, so if you're going to define the probability of the die, of rolling a 1 on a 6-sided die to be 1/6, how do you do that as a frequentist? So you know your approach might be to say, well, in the limit, as you roll this thing like almost infinitely, you know, as the number of rolls approaches infinity, the frequency that this thing's going to happen is 1/6. But as like anyone who studies probability will know, this statement is already relying on some notion of probability. So it's actually not guaranteed that the ratio of those rolls will be 1/6. It's only guaranteed with high probability or as a typical roll sequence. So now you're defining probability in terms of probability, which is no good.
So there's some circularity creeping in there. And also, let me just add one tiny thing, which is if you're going to define probability based on infinite sequences, so an infinite sequence of rolls, a simple property of infinite sequences is that if you take any piece of the sequence, it's not going to be necessarily representative of the entire infinite sequence. Like you could, if there's a probability of 1/5, 1/2 of flipping a coin heads, say, and the first 1,000 rolls are all heads, but then the remaining infinite number of rolls are alternating between heads, tails. Then the first 1,000 rolls has absolutely zero to say about the rest of the infinite sequence.
Right.
Sorry.
Good.
Continue, but just it's
right.
another example of like the kind of the contradictions that start to creep in here. Yep.
Perfect. Yeah. So actually maybe flipping a coin is better. And so what I was saying before is like, you know, probably once you start flipping a coin a lot, as the number of flips that's really big, you're going to see heads approximately 50% of the time. But it is possible that you just see all heads or heads 90% of the time, right? There's nothing in the laws of physics preventing that. And so now you need to have some notion of typicality, like what's a typical sequence of heads to flip. But this is already bringing in the notion of probability. And so that's that's problem one when you start defining things in terms of like long run sequence of events. And then if you just say, screw it, we're going to talk about infinite sequences, then you run into this ratio problem where like, half of infinity is still infinity. So that's a problem. And then you could try and do it with like large but finite sequences, but that runs into its own problems. Okay, but the basic point to get across here is like frequentism has some inherent difficulties, not only when you just try and apply the notion to events that are one-off events, but also just when you try and really rigorously think through even events that are not one-off events. So there's some problems here. And then what you might try and do here is try and salvage this by appealing to some like physical notion of probability. So this is what when I was talking to Mira actually about this, she came up with this. She was like, well, why don't we just start defining probability in terms of like some physical aspects of the die or the coin in this case, right? So you might say, well, if the die is not weighted to any side, it's got 6 sides, it's equally likely to land on any side of the die. So we're going to say the probability is 1/6. You could run a similar argument with the coin. And this is actually a super good thought. And I think this works, but only precisely for events that have some physical counterpart. So then if you start asking, like, what's the probability the day of the week is Monday, if you don't know anything else about the week, then what are the physics of a week? Then you kind of run into problems. So this like physical notion is like a good thought, and maybe is where you try and go next after frequentism fails, but just doesn't work broadly enough for us to apply it to everything. Okay, so that door kind of closes off. And then the Bayesian approach. So I guess just one other thing about frequentism is like what you kind of want at the end of the day is that rational agents, quote unquote rational agents, sort of agree about probabilities and agree about what objective probabilities are at the end of the day. And so Bayesianism kind of turns this on its head. And it just says, well, okay, like if that's what we want to get out of some notion of probability, let's just define probability in the first place. In the first place, having to do with what rational agents believe, and then we'll just see where we get from there. And so this is where you're going. So that's my summary, I guess, of where we are at the moment. And then one interesting, I think, consequence of this Bayesian notion is that probability now is agent relative. So you now only have the notion of probability relative to an agent and his or her beliefs, as opposed to some objective probability. So this is also sometimes called like subjective probability.
Exactly, because this is, I think, such a key point to get across, is that switching from the frequentist perspective to the Bayesian perspective is essentially internalizing probabilities and saying, from a Bayesian perspective, if I'm going to say that the probability of a coin flipping heads is 50%, I'm not referring to anything about the coin. I'm referring to some internal belief state that the agent has about the coin. And so I like to get this point across by saying that the probability of the statement, today is Monday, from a frequentist perspective is 1 in 7, because to say today is Monday is to implicitly assume that there is a set of events. So in this case, the set of events are 7 days. And today is Monday is just saying what is the probability of one event out of the 7 events. From a Bayesian perspective, the probability of today is Monday, there has to be quotation marks around this, because this is the belief that the agent has in the sentence that today is Monday. And that could be anything. So if the rational agent is, or just say it's a baby, born on Sunday, and if it's only seen 2 days of the week and it doesn't know enough about days of the week, then it could say it's 50%. It could say, if it was born on Monday, then let's say it's 100% that today is Monday, and so it's intrinsically subjective. Okay, so that gets us some things. It gets us a coherence when we talk about assigning probability to statements like, what is the probability that the Big Bang theory is true? Or to use your Osama bin Laden example, when Obama asked his advisors what their probabilities were that bin Laden was in the compound in Abbottabad, Pakistan, is that right? To say 65%, say, is them saying that my belief, given the evidence I have currently collected, can be summarized by a scalar value between 0 and 1, and that scalar is 0.65. And that doesn't run into the problems of the frequencies that we discussed earlier, but it runs into other problems, which is, well, who the hell cares what your personal belief is about this? There's a paper by I.J. Good where he's defending this view. It was written in 1975, and it's on my website. And it's the paper which I give the talk on. And he talks about how he's pretty sure that Einstein's theory of relativity is true because all of the best experts in the field believe, given the evidence that they've seen, that it's true. And this is now where my personal opinion is going to start creeping in quite heavily, because I think this is exactly antithetical to science, which is that we aren't trying to produce a bunch of statements that experts believe in. We're trying to produce statements that describe reality. And so before we start going down that particular path, I just want to maybe emphasize that the Bayesian perspective intrinsically prioritizes subjective belief states over objective properties of the world. And some people are okay with that, and other people, like myself, find that to be deeply troubling, because if every scientist tomorrow starts believing in creationism, that doesn't mean creationism is true. It's not necessarily about the beliefs that people have. It's about objective properties of certain theories.
Yeah, I guess maybe I have slightly less of a problem with it than you do, although I do think it's a problem that it masquerades under the name probability, or rather that all of these notions are masquerading under the same name. I think that's causing a lot of the problem here. So when Obama asks his advisors, what's your probability? They might all just be thinking of different notions, right? Like what someone might be trying to quantify their uncertainty, whereas another person's trying to quantify their belief. One other person's trying to quantify just the amount of randomness in the information they were given or something. And so people are, I think, thinking about these notions in very different ways, even on the same day, and all using the same word, probability, and all trying to assign these like scalar values to them. And so I think that's where a lot of the problems start creeping in. But so, yeah, to defend Bayesianism for a second, it is true that it explicitly prioritizes the subjectivity of the agent and isn't overtly concerned with objective truth. But I think if you were to ask most proponents of Bayesianism why they support it as like a system of rational belief, it is probably because they think it gets them closer to objective truth than many other things. So, for example, Yeah, in the Abbottabad scenario, I think what a lot of Bayesians would argue is like, look, if you ask all your advisors for their belief that bin Laden is in the compound, then it's irrational to try and only listen to one of them unless their information source is just objectively better than other ones. But if it's really hard to weigh the pros and cons or the certainty behind their sources of information, then what you should do is just try and come up with some cumulative number that is based on the certainty of all the advisors. And this will probably get you closer to the truth than any one of the advisors individually. And so I think a lot of Bayesians would just take the view that Bayesian reasoning enables you to actually get closer to the truth than a lot of other forms of reasoning, regardless of the fact that maybe it's on shakier philosophical foundations, or maybe more precisely that it uses probability as a notion of subjective belief.
I should. I also want to defend Bayesianism a bit as well, because I guess I should say that I'm in a probabilistic machine learning lab, and I publish in the Bayesian community, and the word Bayesian is unfortunately one of these words that means so many different things and has so many different shades to it. So we're referring to, let's say, Bayesian epistemology. But there's a different kind of Bayesianism, which I'm completely in favor of, in which I would refer people to Andrew Gelman, who's excellent. And he wrote this paper called The Philosophy and Practice of Bayesian Statistics, which kind of defends a form of Bayesianism, which I'm really in favor of. And so I think maybe I can give an example of kind of how they differ and what I consider to be the kind of Bayesianism that I'm a huge fan of, that I use in my day-to-day, and that I hope to continue to work in. There's no good term for it, but I'm just going to, for the purpose of this conversation, just call it Bayesian methodology. So it's a particular methodology to statistics and inference. And just for terminological sake, contrast that against Bayesian epistemology, which is the thing that you and I have been discussing and criticizing. So let me describe Bayesian methodology. So hopefully some listeners will be familiar with just Bayes' theorem, which is just a way to switch the order of conditional probabilities. So P of A given B is related to P of B given A, given a certain identity.
Or maybe just stated as a way of updating belief, just for those who aren't familiar with the mathematical thing. Updating your... Well, okay, but, I see. Okay,
yeah, so you can use Bayesian methodology without having to think about beliefs whatsoever at all. And so,
or rather, just updating some distribution that you have in some.
Sure, yeah. So let me give a super concrete example. So we're living in the COVID era, and one way that researchers are trying to understand how this disease spreads is by using Bayesian statistical inference in the way that Gelman advocates. And so let me describe what that is, which doesn't have to use the word belief at all, and it's a purely objective way to learn about the world. Here's the way that I like to think about it. So imagine you have, imagine the goal is we need to discover what the R-naught value of COVID-19 is. We don't know what the R-naught value is, but we know that it exists, and we want to learn that. And also say that we have a giant software package that simulates the spread of disease. It's a simulator which, given certain parameter values, will produce stochastically different outcomes that we could see in the world. So when I say the word simulator, you can think of just like this giant C++ package, which you press play and you're going to have every person in, let's say, a county region. They're going to have some chance of going to work, some chance of going to school, some chance of contracting the virus, going home, and then you just can run this out, and you can basically just press play and get a whole bunch of data out that looks kind of like the world that we see right now. And so now say that you have two different hypotheses that, for simplicity's sake, let's say that we think that R-naught is either going to be 1 or 2, just for simplicity's sake. So what we're going to do is we're going to put in R-naught equals 1 into our simulator, press play, get like 100,000 samples, 100,000 examples of what the world would look like if the R-naught value was 1. And then we're going to contrast that to what we actually see in the real world, and we'll just get rid of all of the simulations which don't match what we see. So let's say you put in R-naught equals 1, you run the simulation 100,000 times, and 70,000 of those produce data which kind of looks like what we're currently seeing in the real world. And then you put in R0 value is 2, and you do the same thing, and then you get 30,000 simulations that match what we see. Then we're going to say that the chances of R0 value being 1 is 70%, and the chance of R0 value being 2 is 30%, just by simulating the world, pruning out all those simulations which don't match what we actually see, and calculating the relative frequencies of these two values. So this is Bayesian updating. This is Bayesian methodology, where the parameter value R0 is going to be our prior probability. The simulator is going to be what they call the likelihood. And then on the other side of this, you get now a new distribution over the input parameter values that is, just created based on frequencies. This is, the word belief didn't have to creep into this at all. It's simply just a way to generate data that looks like the data that you see in the real world. And then you use the generated data to infer, and that's why people use the word inference, infer what we likely think the parameters are that we don't have access to look like. So this is what I'm going to, just for the purposes of this conversation, say is the kind of Bayesianism I'm a huge proponent of, because it's a completely objective thing. And notice also that it uses frequencies. It's using Bayes' theorem, described as Bayesian, but it's just using simulations and frequencies in order to infer the underlying parameter values the latent variables that we don't have access to. So I wanted to say this because I wanted to defend a kind of Bayesianism which is entirely objective and and should be distinguished between the side that we're criticizing, or at least that I'm criticizing.
Yeah, I just maybe to start differentiating these, I'd like to just throw an example your way and just see how you handle it. So let's say I've been I just wake up and I've been in a coma for the past 6 months or something. I wake up in the hospital bed, and let's say we're interested in my belief about what day it is of the week. Okay. Here I just wake up from a coma and I don't know how long I've been out. So a Bayesian might argue it the most rational belief for me to have about what day it is, maybe that it's Monday, is 1 out of 7. So I have no reason for thinking it's Tuesday rather than a Monday rather than a Thursday, for example. So my prior probability distribution, my prior belief about the scenario is that it's equally likely to be any day. So now the doctor comes in. Let's say the doctor says, well, tomorrow, just in an offhand way, says tomorrow's the start of a long weekend. Mm-hmm. And I say, oh, interesting. So how does this factor into now my belief about what day it is? Well, long weekends, it could start on a Saturday and be that Monday is the end of the long weekend, or Tuesday. Mm-hmm. Or it could be that the long weekend starts on a Friday or a Thursday. Mm-hmm. But it's rare that the long weekend would start on a Tuesday, so that today's Monday. That's just doesn't happen as often. So now this might start changing my belief about what day it is. So now I'm probably well, it's probably not Sunday or Monday. That would be odd. Probably not Tuesday either. Could be Wednesday, Thursday, Friday. Those all seem more likely than the alternatives now. Mm-hmm. And so this is my Bayesian update now. So I had some prior belief. The doctor inadvertently gives me some new information, and then I update my belief about what day it is. So what is do you have a problem with this example, or what's your take on this?
That is kind of the story of what Bayesian updating is. And I use that story in some modes when I'm working with Bayes' theorem, because sometimes it's very useful to think about conditional probability as the belief a certain agent has in a proposition given the evidence that they've seen. I consider that story to be a useful tool for analysis, a useful metaphor for thinking about some kinds of mathematics. Do I think that this is what is actually happening in the human brain? Do I think that the human brain forms beliefs in accordance with the sum and product rule? No, I don't. I think that there's arguments to be made that this is not what the brain does, and perhaps we can get into some of these arguments. So I don't have a problem with that story if it's just seen as a metaphor, a useful way to think about some of these equations. But I think we start getting into trouble when we take it too seriously. I also think that if we're going to be programming agents, let's say a Roomba in a room, it's really useful mathematics to get robots to negotiate in their environment. So it can be quite useful, and it's a useful tool for thinking, and you can use it like Kalman filters. And there's all sorts of like deployed systems which use this math, and it's great. But where we start getting into trouble, I think, is when we start taking this too seriously and think that this is literally what the brain is doing. This isn't a straw man. This is something called the Bayesian brain hypothesis, which says that Bayes' rule is what the brain is actually doing. And this is what some people are pushing quite hard on as their best bet for what's going to get us AGI. So perhaps we can start moving in that territory. But what I do with that example is just it's a useful heuristic. It's a useful thing to know, but it's something that we shouldn't take literally, I guess.
I guess I just want to really try and clarify what I think we've given like sufficient background, at least hopefully, I don't know at this point. But I think, we really maybe want to clarify your problems with probability theory and exactly what you mean. Well, I think last time you said probability is not a coherent concept. Obviously, correct me if I'm misquoting you, but that we kind of want to course correct and not even rely on probabilistic epistemology anymore. Obviously, we need probability as a mathematical tool to do useful things, but we want to. It's time to throw it out as a tool of epistemology. And so I guess what I'm trying to discover with this example is, regardless, it seems not relevant to me that you don't think it's what the brain should be doing, or at least is doing rather, or at least maybe that just seems like a separate conversation. But there is a claim to be made about what the agent should do in this scenario. Should they believe? And can we call this probability or not? And I guess I'm trying to discover, like, do you have a problem inherently with the notion of a probabilistic belief of an agent? Like, do you think it's problematic that the agent is sitting there trying to form some probability distribution of what day they think it is? Or do you have a problem with how they go about doing that?
Yeah.
Sweet.
So, what time is it? Did I get about an hour into the podcast before mentioning Karl Popper?
My God, it's a record.
So I think to answer this, I need to pivot and talk about the logical concept of content and Popperian epistemology. And then we can see that these two views of the definition of rationality and what agents should do are in direct contradiction with one another. And so I think to answer your question, I need to at least propose an alternative thing and framework for thinking.
Great. All right.
And so I just love this idea of content. So what's content? It's a logical concept, and it's quite easy to understand. So the content of a proposition, so a sentence, a statement, is just the class of all logical consequences of that sentence, statement, proposition. I'm just going to use the word sentence because it's the most plain. So, for example, the content of the sentence, "It is Monday," would be sentences like, "It is not Tuesday," "It is not Wednesday," "It is not Thursday," etc. The content of the sentence, "DNA is wound as a double helix," would include sentences like, "If you shine a laser through it, you'll see a certain projection of a shadow pattern on the wall." That's just a direct logical consequence of the sentence. So we can talk coherently about the content of propositions, and we can start to see that it matches on to our intuitions a little bit. So the content of a tautology is zero. So the content of the sentence A equals A is zero because you get nothing out of that. The content of a contradiction is, let's say, just for simplicity's sake, let's just say that we can assign a measure to it. So we'll just say that the content of full maximum content is 1, just for simplicity. And the content of a contradiction would be 1, because from a contradiction you can derive anything, which is just a simple consequence of logic, that from a contradiction anything can be derived. But it's therefore false, because you can derive a sentence which is refuted by reality. Let's keep exploring this a little bit more. So then the content can be split into logical content, which is all, like, the entire class of things which can be derived. I should also perhaps say, when I say derived or is a logical consequence of, What I mean is simply that if we assume the truth of the proposition, let's say if we assume that today is Monday is true, then a logical consequence is like a truth broadcasting operation. So given the assumption of truth, a logical consequence allows you to broadcast that truth to the other sentence. So certain logical operations are invalid precisely because you can't let the truth flow from proposition to proposition. So that's what I mean by logical consequence. So content can be split into logical content, which is all of it, and then a subset of logical content is empirical content, which is statements which can be contradicted by the world that we see. So once you get into this space of thinkers, the swan example comes up almost immediately. So let's use swans as the example. So if my statement is all swans are white, the logical content of that sentence would include things like there are no black swans. Fine. Empirical content would be there are no black swans in Vancouver, British Columbia at 6 p.m. on Thursday in this particular square. That's something which would flow from this. And so that's an empirical content because that can be falsified. So you can go and you can check, and if there is a black swan, then truth broadcasting flows forward, but falsity broadcasting flows backwards. So you always assume truth, then you can check if the empirical content is verifiable. And then if you find out that it is contradicted, then you know that your assumption of truth is false. And so, okay. So
empirical content is a subset of content.
Yeah. So let's keep developing this a little bit more. We can then talk about the content of metaphysical statements. So the content of metaphysical statements has logical content. So for example, the one that I've used is the arc of history bends towards justice. That's a metaphysical statement because there are consequences which can be derived, such as the future will be more just than the past. But there's no empirical content because there's nothing that can be falsified by that. So philosophy tends to play with metaphysical statements which have content and are valuable but can't be falsified. Okay, so how does this relate to probability? And this is going to start getting closer to your question. So it's quite easy to see that if you take two statements with a certain amount of content, let's say the statement, it is Monday, that has some content, and the statement, it is raining, that also has content. The conjunction of these two things is going to have more content than the two things individually. So it is Monday and it is raining directly implies it is not Tuesday, but it also directly implies it's not sunny. And it also directly implies that buses will have windshield wipers on because buses run on Mondays and if it's raining. So you get more out of that conjunction. But the probability of a conjunction goes down. So if you have two statements, it is Monday and it is raining, there's certain probabilities associated with both of these two statements. But when you conjoin them, the probability goes down. The probability of a tautology is 1 because it's always true. And the probability of a contradiction is 0 because it's always false. So probability calculus, by which I mean completely independently of the frequentist or the Bayesian interpretation, it's just sum and product rule, sums to 1, that kind of thing. As the content goes up, the probability goes down, and vice versa. So this is where Popper comes in because he states, and I agree with, that the point of science is to produce sentences with high content. Sentences like, you cannot travel faster than the speed of light. That is a sentence with a huge amount of content in it. That has direct implications about time and space. And we, as rational thinking human beings, are capable of producing sentences with high content. And in science, the thing that's most highly prized are bold, high content theories. Bold in the sense that they have huge amounts of empirical content and take, therefore, a lot of risks because every time you shine light through a double helix, you are essentially risking the falsification of this theory. So what does that mean? That means if we want in science to produce theories with high content, we therefore must also need to produce theories with low probability because of this relationship. And so Popper makes the point that if the goal of science was, in fact, to produce statements with high probability, then our textbooks would just be filled with tautologies. All we would want is tautology after tautology, because tautology is, by definition, high probability. But we don't want that. We want theories with high content. And so this is where I can actually answer your question, which is human beings are uniquely capable of producing statements about the world with high content. And this is the project of the scientific enterprise. And it has always been like this, and it hopefully will continue to be like this. But that means that we should not be so quick to use the probability calculus to determine what is rational, to say that what is rational for an agent to believe the laws of rationality have to be governed by the calculus of probability. So now onto your specific example of a person wakes up in a coma. Yes, you can use the metaphor of probability to say, like, how should they update their evidence? But you can also think about it with entirely different language, and you can think about it in terms of trying to figure out what is true, independent of their beliefs. And we can think they had a particular view of the world, which was that it's Monday. That view was disconfirmed was falsified. The evidence was tomorrow is going to be a long weekend. And this is the process of conjecture and criticism. And so this is why I have problems with Bayesian epistemology, because we have this other logical framework called content. It's not nearly as developed. Popper wrote about it in the 30s and 40s, and I think it hasn't really been worked on. But I don't think we necessarily must assume that the calculus of probability is the best way to describe the products of human cognition. And so this is why I'm so interested in this, because of the subject of AGI. Nobody knows what the hell intelligence actually is, or what general intelligence is going to be. But I think a good reason to be suspicious of the calculus of probability as being the thing which is going to get us there is that human beings can produce statements with high content, and I just simply do not think that the rules of probability are going to produce things like DNA is structured as a double helix. And so we need to figure out what it is that allows the human brain to produce these things. And I'm not convinced that the calculus of probability is that.
That was good. I think we should
come back at me.
What I think it's worth, regardless of my impressions of how this relates to my example, I think it's really worth pausing just to talk about the implications and the substance behind what you just said and how it relates to scientific discovery. So, that was really good. So, the idea that we're trying to produce theories that have high content, I think, is relatively agreed upon. You know, people value theories that can make bold predictions, and our most prized theories are precisely those that deviated from the knowledge base at that point, went out on a limb, and said some stuff that was viewed as highly contentious, and that just proved to be right. So obviously, famous examples, Watson and Crick with the double helix, Einstein's theory of relativity, germ theory of disease, all of this stuff sounded crazy, but was proposed forcefully anyway, and then has not yet been falsified.
If I may just add something to that, not only did it sound crazy, but the theory came first, and then evidence was gathered to try to falsify the theory. But the Bayesian view would have it be the opposite, which is that evidence comes first, and then the theory kind of is formed after the evidence. So evidence comes in, theory changes, and so it goes. But I think it's exactly backwards, is we have a theory, and then we seek out evidence that disconfirms that theory. And so the order of operations, I think, is also incorrect in the Bayesian view. Sorry to
right. On this view, you want to push out as many explanations as possible, and then let empirical prediction falsify as many of those explanations as possible, and then you're left with the best explanation that is standing. So on this view of science, what is prized is more hypotheses, more creative hypotheses that try and explain all sorts of phenomenon. But I think so what I was saying before is I think people at least intuitively understand that what we value are maybe, or at least theories that predict a lot that are possibly highly contentious. But I think the fact that this directly implies that what we don't want to produce are theories in which we are as confident as possible has not maybe been grasped by people as much. So this is what blew my mind I think, when reading Popper, is that if the goal was to produce theories of which you were the most certain that they wouldn't be falsified, you would barely deviate at all from what is currently known.
Exactly.
And you would certainly not risk putting out a theory that had all sorts of novel content that risked being falsified by myriad different things.
To interrupt you slightly, can I read a quote from Popper? And then continue, just because I actually have this quote up on my screen, because I look at it every morning before I wake up and once I go to bed. I'm just kidding. So
those tattooed on the inside of your eyelids.
So those who identify confirmation with probability must believe that a high degree of probability is desirable. They implicitly accept the rule, always choose the most probable hypothesis. Now, it can easily be shown that this rule is equivalent to the following rule: always choose a hypothesis which goes as little beyond the evidence as possible. And this, in turn, can be shown to be equivalent to always accept the hypothesis with the lowest content within the limits of your task. I'll end the quote there, but this, I think, is one of the things that you're referring to with Popper, which is, like, if the goal is to update your beliefs based on the evidence, then you want your beliefs to be as tightly matched to the available evidence as possible, rather than trying to make really bold, groundbreaking, like what's a breakthrough? A breakthrough is where everybody in a field believed one thing, and in fact something else was true. So a breakthrough tends to not come because there's so much evidence available that everyone's beliefs get updated such that we now have a breakthrough. It's that somebody has the audacity to think differently from all of their peers, and then upon having this idea, go and collect evidence to basically make this idea inignorable. Sorry, I cut you off, but I just wanted to kind of provide a quote for those still listening, kind of about what you were saying with Popper's claim there.
No, that's great. Okay, yeah. So this is also a little bit of the distinction, I guess, between like confirmation and falsification in terms of how we view scientific progress. So your approach really underscores falsification as the mechanism to make progress. So you want to come up with as many theories as possible, and then seek to falsify them with evidence. And in this way, you are left with the best explanation standing, or possibly no explanation if you have no explanations. But you have the best explanation at a time of a phenomenon. And as we understand more and more, we seek better and better explanations for phenomenon. And this is the view of how we make progress. Okay, yeah. So I guess returning to my example, so it seems to me that you want to say the way, or the methodology, the psychological methodology that we use to make scientific progress should also be applied at the personal level. So when we're seeking beliefs about the world. So when I'm lying in the hospital bed, instead of thinking about how to update my prior belief in the best way possible, I should be conjecturing possible explanations as to what day it is, and then seeking to falsify those.
That's exactly right.
All evidence available to me.
Beautifully summarized view of my position. That's exactly right. Yes.
And so, but it doesn't seem, so maybe I haven't thought this through, but it seems possible to me that someone might hold that Popper's falsification is the proper way to make bold, or rather scientific progress at the academic level, but when it comes to your personal beliefs in very constrained areas, Bayesianism is certainly the way to approach the problem. So, in the example where you're lying in the hospital bed, it's unlikely that there is a solution to the problem that has not occurred to you. It's probably not some day of the week that doesn't exist. It probably is either Monday, Tuesday, Wednesday, Thursday, or Friday. Or Saturday or Sunday.
But not Saturday and Sunday.
Definitely not those days. And so in this case, it seems to me possibly appropriate to use the Bayesian ways of updating, because all the possibilities are sort of there in front of you. What do you say to that?
Yeah. Oh, so good. Oh, I love that comment and that question. So you absolutely got me perfectly correct, which is that I make no distinction between kind of the ordinary, everyday actions of us and the grand project of science. I think it's all unified. It's all exactly the same. And when I talk about science, I think that I should have previously not only used Watson and Crick and Einstein and these groundbreaking thinkers, but also you're at home and you have to figure out why your toilet isn't flushing correctly when you press the flusher. And so you think, maybe the flusher isn't connected to the handle properly. And so you make a little conjecture like, but this is probably what's wrong. You open it up and you realize, no, it's connected properly. So then you think, okay, well, maybe it's that the plastic latch thing is broken. And then you check that. And then you find that that's also wrong. And then you think, no, maybe it's the fact that the stopper is disconnected, and you go, okay, I'm done with the metaphor.
Your anatomy of the toilet, your knowledge of the anatomy of the toilet.
But I mean, every single thing that, like, it's just problem solving. It's just problem solving. When you code, this, I know example is going to lose a good portion of the audience, but when you code, the whole thing is just like, shit, this isn't working. What's a guess as to why it might not be working, and then you check that guess. When you are communicating with your spouse and you are in an argument, and the whole game is you're trying to guess what the other person is thinking, and then you say something, and they respond in a way that indicates that you've completely misunderstood what they're trying to say. And all we can do is guess and check. It's guessing and checking all the way down. That's the only process we can do. And perhaps this is slightly a tangent, but I think it's an interesting one. What is the very process of communication that you and I are engaging in right now? When two people are communicating, I say a bunch of words, and you have slightly different definitions of these words in your mind, but you've read similar stuff to me. And then you guess, and you summarize, and you repeat back to me what you think I'm thinking. And then I say, oh, that's perfectly right. And then you've confirmed in your head that your conjecture about what I'm thinking is accurate. Other times, I'll get it wrong, where I say to you, okay, this is my impression of what you've just said. And then I say it back. That's a conjecture about what it is you're thinking. And then you say, no, that's totally wrong. And this is the whole process from the very top to the very bottom. When you read a book, you are actively trying to guess what it is the author is saying. And that's why good writing makes that process very easy, because the guesses are quite quick. But poor writing leaves you constantly guessing, and there's nothing to verify back. And poetic and beautiful writing kind of stimulates you to guess all sorts of things which there's evidence for, but isn't totally confirmed or disconfirmed. It gives you a whole playground of guesses and connections to be made. But it's this process all the way down. Yeah.
Okay. Yeah. I guess I just want to clarify a couple things. So there's two things going on. One is how we should be obtaining new knowledge. One is how we do. Yeah. So there's and these are distinct things. So it could be the case that how we proceed in our daily lives, how we problem solve on a day-to-day basis, is sort of this Popperian approach. But the best way to do it might be Bayesian, or it could be vice versa. And your examples, I think, were bouncing back and forth between the two. So you said, the way we are in a conversation right now is more or less a Popperian approach. And so that could be the case, but it could be that I'm not even sure what a Bayesian conversation would look like exactly. But so I just want to clarify that you think both that the way we typically do engage in problem solving is this epistemology based on falsification, and that this is the proper way to achieve, to reach truth.
I don't want to say it's, quote, the proper way. I'm not...
Or the most effective way, perhaps.
Yes, okay. Yeah. So it's the only way that we currently know how to approach truth. Whether or not it's proper is something I'm less interested in. If guessing and checking is all that I'm saying we do. But within that, there's all sorts of space to guess in different ways. Like you could go into a float tank with a bunch of hallucinogens and get a whole bunch of guesses, and then go check based on a completely new method. And that's all completely fine. I'm not making any statement about what kinds of guesses are allowed and what kind of checks are allowed and proper and right. And this is actually one of the things that I dislike about some aspects of Bayesian philosophy, because it essentially asserts that this is how one should be rational. It gives a statement about what rationality is. It says, if you do not act in this particular way, you are not acting rationally. And you could say the same thing about what I'm saying, except I'm not prescribing one does anything. I'm just simply saying that this is what we are doing, and we should be aware of the fact that we are doing this, and knowing that this is the thing that has produced both a new toilet and also a new theory of space-time, I think allows us to continue this process, but also not... that's maybe too strong, but it makes me more skeptical of opposing theories of what rationality is and should be that are predicated on certain prescriptive, here's how you have to be rational rules, which I don't think maps onto what people actually do in the real world. When you and I are communicating, we're constantly guessing and checking. This is something that is evident to hopefully both of us, and you can just play back the tape, and the whole thing is just guessing and checking, guessing and checking. This is why we repeat back to one another. But I don't know what it means when someone says, I have now conditioned on the evidence and I've increased my credence from 0.54 to 0.56. I don't know what this means. This is just, it's a mode of speaking that I think upon reflection doesn't map onto what people are actually doing. So, yeah.
Cool. I don't know. Do you think we've confused people enough for a single episode, or
how far have we gone? I guess maybe closing thoughts.
I think it would be useful to return to it. I think I'd like to try and give a robust defense of Bayesianism, or at least reasoning in this way. I think that would be fun and useful for my own thinking, if not for other people's.
100%. Yeah. I totally agree. I think it'd be good to re-listen to this conversation, see perhaps where we were talking past one another and which areas we missed and didn't miss, but and hopefully get into more of an argument because it was too much agreement.
But I think hopefully it didn't lose people. If you were lost, send us an email swearing at us.
Yeah, exactly. I think this is a lot of fun. Let's definitely continue the subject next time, and hopefully get to the bottom of it.
So. Sweet, sounds good.
Sweet. Cheers, man.
Yeah, take care.